The first big topic that we're going to talk about in this class is wheeled robot control. And we specify wheeled robots because there are just so many different types of robots. I list a few of them here. Wheeled robots are, kind of self-explanatory. They're any robot that moves with wheels. So self-driving cars would be a wheeled robot. The robot we looked at in class earlier was a wheeled robot. There are other types called manipulators, and those are kind of like the technical term for robot arms. Those are a whole class of robots in themselves. They're legged robots. These are typically robots that are moving on the ground but not moving with wheels. So think of like humanoids, or you may have seen like cheetah robot videos over the last few years. And then of course there are aerial robots, and these are just any robots that fly, and drones comprise the largest percentage of those kinds of robots. But we're just going to be focused on wheeled robots for this class. And even within wheeled robots, there are quite a few different types. Here are just 4 common types. On the far left, we have differential drive robots, which is what the Turtlebot 3 is. It has 2 wheels moving independently of one another. And shown here, I have the base of the Turtlebot 2, which also is a differential drive robot. Carlike robots are, of course, wheeled robots. There are a couple others called skid steer and synchro. We won't really work with any of those in this class, and we won't even really mention them much. If you continue in the robotics industry, you'll probably encounter them, but for this class, we're mostly going to be considering differential drive, and we're going to talk a little bit about the theory of car-like robots, but we won't be actually working with car-like robots. So let's start by just defining differential drive robots. These robots are any wheeled robots where there are 2 wheels that are controlled independently by their own motor. So if you flip that robot upside down, you'll see it has a left wheel and a right wheel, and each of those wheels has its own motor that can control it. So the left wheel can move independently of the right wheel, which means it can move with different speeds and in different directions, and of course the right wheel can do the same. So typically the input to these robots are a left wheel velocity and a right wheel velocity. And when you pass in some velocity, the motion that occurs can be partitioned into like 3 different types. So if the wheels are moving at equal velocity, so the same speed and in the same direction, you're going to get straight line motion, so like forward or backwards. If the wheels are moving at opposite velocity, so like the same speed but different directions, it's just going to turn in place. And anything else is just some type of curve, some type of 2D curve. It could be a circle, but it's not limited to a circle. It could be like Bezier curve, could be a like a polynomial spiral. It's just some type of curve, and things get really interesting when you try to plan out specific types of curves for the robot to move on. The feedback for these kind of robots is going to be largely based around wheel encoders. And wheel encoders are kind of like the bare minimum sensor for wheeled robots. A wheel encoder tracks how much a wheel turns. So I have this like really small and simple picture here on the left where you're looking at kind of like the side view of a wheel, and you see all these little lines going across the full circle. And then if you look on the right hand side, there's one like little notch that's like kind of outside, like on the outer rim. And so if you can imagine, as the wheel moves, you can track like how many notches pass that outside notch. And if you know that information, then you can start tracking how far has this wheel turned. If I know that there are so many total notches in my wheel encoder, and X% of them have been passed, then I can have a pretty good idea of how far the wheel has been turning. And if you know how far the wheel has turned, in terms of like radians, and the radius of the wheel, so like the physical size of the wheel, you can compute how far the wheel has moved on the ground. So if you think of a wheel that maybe has circumference like 1 meter, which is a pretty massive wheel, but let's just say it has 1 meter, and you can detect that it's moved one full circle, that the thing that is on top of that wheel, what that wheel is carrying, has moved 1 meter forward. So you can actually detect, how far your body or your robot is moving in the real world just based on this pretty simple information. And you can, of course, also detect how fast the wheel is moving if you just poll this information a few times and detect the distance over time. And so typically the only information that we have about wheeled robots whenever we're just using wheel encoders is the number of ticks that the right wheel has gone through and the number of ticks that the left wheel has gone through. But from that really basic information, we can actually compute odometry. And what odometry is the position and orientation of the robot. So essentially the geometric representation of the robot. So where is it in the world? And that's what you're going to be doing in class next week. You're going to be taking in these wheel encoder values, and you're going to be outputting the odometry information of the robot, the position, the orientation, and we can even compute velocity with encoder ticks as well. So you'll be computing that in addition to just the position and orientation. So the first thing we need to know is how do we tell how much distance has been traveled by a wheel simply based on encoder information. So we're going to set some variables to do that. C is going to be the wheel circumference, so the distance traveled by the wheel in one revolution. Q is going to be the number of encoder ticks per revolution, and SIT is going to be the encoder tick that that was previously returned by the encoder for wheel I at time t. So if we want to get the distance that the left wheel has traveled, dl, we're going to say SLT, so the encoder tick we just passed on the left wheel at time t, minus the previous encoder tick that we got. So kind of like the delta S, basically. So the change in encoder ticks. We're going to divide that by Q, which is the total number of ticks per revolution. So we're kind of getting like a percentage of the total revolution, and then multiply that by the wheel circumference. And the wheel circumference is an actual length unit, so something like meters. And so when you multiply C, you get the actual distance in meters or whatever length unit you want to use. dr is basically the same equation, except instead of SL, we have SR, but we take the latest encoder tick, subtract it from the previous encoder tick, divide by Q, and multiply by C. And that gives us the distance that the left wheel has traveled, the distance the right wheel has traveled, and then we can start thinking about, okay, how do we actually use this information to give us the change in geometry information, which is position and orientation. So so now we'll take a look at how we actually model differential drive robots so that we can actually compute odometry information. So we start by having this outer circle that represents the whole robot. I put these two little rectangles here. Each one of those is a wheel, so a left wheel and a right wheel. And then I have this point in the center, and that's meant to be in the center of the two wheels, and that is referred to as the reference point. So anytime we say reference point, what we mean is that is what we are considering to be the XY position of the robot. So if I say the robot is at position like maybe 1, 1 or 3, 2, what I mean is that the reference point of the robot is at that position. The rest of the robot can be, that's going to, of course, extend beyond the reference point. But when we say, okay, the robot's position is these two values, this X value and this Y value, what we're referring to is the reference point of the robot. So another thing that we need to know about the robot is the distance between each wheel in the center of the robot, or the reference point of the robot. So we're going to label that as RW. And as the robot moves, anytime it drives on a curve, you can actually represent the motion with a circle. So even if the robot doesn't move on a circle exactly, if you break down the movements into small enough little steps, you can model it as a circle. And so the circle is going to have radius r, the big R you can see down here in the bottom left, and that's going to extend from the left wheel of the robot to the center of the circle. And then we're going to have some delta theta, and that's going to be the arc that is, that has been covered by the robot as it moves on the circle. And we can add a few more variables here. So dl is going to be the distance that the left wheel has traveled. Dr is the distance that the right right wheel has traveled, and then d is the distance that the reference point on the robot has traveled. And all of these are represented with the circular arc formula. So if you look at dl, you can see it is equal to r times delta theta. So this r is the overall radius of the circle, and then we have this delta theta, that's the angle of the arc that we're moving on. And if you look at d, it's the same formula, but the radius value is a bit larger. The reason is that the reference point is farther away from the center of the circle than the left wheel is. So we have to actually add this RW value, the distance between the left wheel and the reference point. And then it's a similar thing with dr. dr is even further away, so we actually have to add 2RW to the radius for this formula. But most of the time we don't actually know delta theta, and we're actually trying to compute both d and delta theta. So even though we have those formulas, they're not we can't compute them directly. So the only information that we have about the robot is dl and dr, and we get that from wheel encoders, and rw, and that is part of the rw is part of the physical structure of the robot. So that is something that we always know. So we have to solve for d and for delta theta. So the two equations that we have are the equations for dl and dr. So we have two unknowns and two equations. We should be good to go. So let's solve for delta theta first. So I list the formulas here, or the equations for dl and dr for reference. So we are going to take dr and we're going to rearrange it a little bit. So then we get delta theta and rw on the left hand side, and then the rest on the right hand side. And then we can easily just divide by rw and isolate delta theta. And so delta theta is actually going to be the right wheel distance minus the left wheel distance over 2 times rw. So now we need to solve for d. So I list these equations up here again just for reference. And the equation that we have for d, that we know, in theory, we know that d should be equal to this, is the circular arc equation, so r plus rw times delta theta. So we can distribute out this delta theta. We can rearrange the dr formula to get dr minus dl over 2. And then we just go through these steps. I don't want to go through every single step here. I will leave it to you all to make sure that you can follow these equations. If you have trouble, you can come talk to me. But in general, you should be able to follow these. And at the very bottom here, we get all the way down to d equals dl plus dr divided by 2. And so what's really neat about this is that given only the distance that each wheel has traveled, which again we get from encoder information, we can actually calculate the change in position and orientation for the robot. So recall that our equations for dl and dr are these two shown here. They're based on the encoder ticks, the wheel circumference, and the number of ticks for 1 revolution. And given that low-level information, we can actually compute a higher-level geometric information about the robot, which is the change in the orientation as it moves and the overall distance that it's moving. So now we can calculate the change in global coordinates. So we have the robot over here on the left, and it has some position and orientation, and then it moves to this position over here on the right. And so this position on the right, we know that is going to be d distance away, which is nice. But what is really helpful to us a lot of the time is to know what's the actual change in x and what's the actual change in y. And luckily, these values are pretty easy. Oh, I should say real quick. Previously, I was representing d with a curve. Now I'm representing d with a straight line. The reason is that whenever you are trying to gather odometry information, it is normally computed very fast, like 20 to 30 times a second, sometimes even up to like 50 or hundreds of times per second, depending on how serious your application is. And in those time steps, we represent the robot's motion with straight lines. So even though it may be moving on a curve, if we're measuring all this like 1/50th of a second in 1/50th of a second time steps, we can model that distance as a straight line here. So here d is a straight line. And that's really nice because now we can just use trigonometry, just basic trig to solve for delta x and delta y. We just have d cosine theta and d sine theta. So we should formalize this a little bit more, specifically using linear algebra, because in robotics the most formal way to represent things is using linear algebra, because we tend to end up with a whole lot of equations. So down here in the bottom left, I have two positions of the robot, two positions and orientations. The first one is p, and that would be a 3x1 vector, x, y, theta. That's the x and y value of the robot and its orientation. And then we have this other position and orientation called p prime. So in order to compute p prime, I have this equation up here in the top left. P prime is going to be this 3x1 vector, x, y, theta, plus another 3x1 vector. And that 3x1 vector on the right, you may recall, is going to be that's the formula for delta x in the first element. The second element is delta y, and then of course we just have delta theta right there. So as the robot is moving around, we're always using this equation in the top left to compute the new position and orientation of the robot, and I put the equations over here on the right hand side. Okay, so as the robot moves, we can compute its position, but we also have to consider its velocity. So as the robot moves, it's going to have some overall linear velocity and angular velocity. And we can compute the velocity semi-easily, but really what's most useful to know is the velocity along the x direction and the velocity along the y direction. So as the robot moves, it may start over here on the left, and then I have this new position and orientation here on the right. You can see that we can represent the motion with a straight line, and within the straight line the robot is going to be moving at some velocity v, and it's going to have some orientation theta. And by the end of its motion, it's going to have some new position and some new orientation. So in order to compute x dot and y dot, we just use basic trig again. So v cosine theta, v sine theta. But kind of similar to the position issue where we didn't really know d, we had to solve for d. We have to do the same again, but solving for v. So the things that we know are the left wheel velocity and the right wheel velocity and the wheel radius. The wheel radius here, small r, is the physical size of the wheel. And remember that this matters because we have to, bigger wheel sizes are going to move slower or faster than smaller wheel sizes. So the size of your wheel is going to affect how fast your robot is moving. So v is actually pretty easy to compute. I'm not even really going to bother trying to solve it. I'll just show you the equation. VL plus VR divided by 2. So essentially it's just the average of the two velocities. And theta dot is going to be a little bit more complicated, but not too much more. On the right hand side we've got these kind of two parts to this term. So we've got the wheel radius r over 2 rw. And then we've got VR minus VL. And so the thing that I just want to point out here is that whenever we're computing the velocity, keep in mind that we also have to compute the direction. And that's easy to remember with linear velocity, but it also matters for angular velocity. And that comes into play here on the right-hand side of this term with the stuff in parentheses. So VR minus VL. So if the right wheel is spinning faster, that means that VR would be greater than VL. And you can try to imagine a right wheel spinning faster than a left wheel. That's going to push the robot to the left. It's going to kind of curve it over to the left. And when it's curving over to the left, if you think about the robot being at orientation 0 and then curving off to the left, that's actually going to be rotating counterclockwise, which in general is what we think of as positive angular rotation, so positive angular velocity. If the opposite were true, VL were larger, then this part in the parentheses would end up being negative, and that would lead to the robot moving to the right. So if the left wheel was faster, the robot would be curving off to the right. And if you think about it, initially having some orientation 0, then it would be rotating in the negative direction. So something we talk about a lot in robotics is control. And I didn't really talk about control at the beginning because we're not really going to talk about control very much in this class. Control theory is a very large field. You study it a lot in the mechanical engineering domain and some in the electrical engineering domain. And what it is like trying to define a set of equations to say, if I pass in these values to these inputs, I can compute then kind of exactly how my system is going to move or how my system is going to react. And it's a very big field, very important field. We're not going to talk about it too much, but I do just want to show you what we would consider to be a control system for a differential drive robot. So the control system is concerned with moving the robot. So we're concerned with the velocity, not necessarily the position of the robot. And over here, we have, on the far left-hand side, we have this 3x1 vector again, x dot, y dot, theta dot. And in the middle, we kind of plug in the simple version of the equations, which is, v cosine theta, v sine theta, and then the theta dot equation. And then we just expand these out over here on the right-hand side so that all of our inputs are just the VL and VR. So if you look at these equations on the rightmost vector, the only variables we have are VL, VR. Again, we have little r and we have RW, but keep in mind those are static constant values. The only things that are changing in these equations are VL and VR. Okay, so this 3x1 matrix here, we would consider, maybe not to be the full control system, but essentially what we're talking about here is how to control the robot. Any people in mechanical engineering can tell you much more about control theory if you're interested. So I just briefly want to talk about carlike control, or control for carlike robots, how we kind of represent motion for a carlike robot, or how we define a set of equations that tells us how to move a carlike robot. And I'm just going to jump straight into the velocity values. I'm not going to spend much time talking about how to compute odometry for a carlike robot, because it's pretty similar to how we compute odometry for a differential drive robot. I might go as far to say that it is the same, but I would maybe have to double check before making any definite claims on that. But at the very least, it is very, very similar. If you are interested, you can go look up, computing odometry for carlike robots. So first, let's talk about this model of a carlike robot. So I have a really basic carlike robot here. And carlike robots, they have two sets of wheels that are connected. So two in the front, two in the back. So the two wheels up front are connected. They're always in the same direction. The two wheels on the back are connected, and they are always in the same direction. The reference point for a car robot is almost always going to be this point between the two back wheels. So I put this little point here, and I have these dotted lines to show that this is where we're considering the X of this robot, and this is where we're considering the Y of this robot. And the orientation of the robot, the overall orientation, is actually going to be the difference between the direction of the back wheels and the x-axis. So you can see that the back wheels are kind of facing in whatever direction the overall car is facing, and so the difference between that direction and the x-axis is going to give us our theta. We also have this value L. L is going to be the distance between the two sets of wheels. That matters whenever we're considering how fast a car can turn. Smaller cars with a smaller L value they're going to have a smaller turn radius than cars that have a large L value. And then we have this other angle value up here, phi or phi. I never know which one people prefer. I'm going to call it phi. So phi is the direction between, it's the difference between the direction of the front wheels and the direction of the back wheels. And this value is controlled by the steering wheel. So as you drive a car around, you're moving the wheel, and what you're actually moving are the two front wheels, Yeah, with some exceptions. So in general, I know there are cars that do other stuff, but in general, most cars, the vast majority of cars, you turn the steering wheel, you're going to just be turning the front wheels. And so we're going to have this difference between the front wheel direction and the back wheel direction. And that angle is represented here by phi, and it's referred to as the steering angle. So the control system for a car-like robot is going to look something like this. We want to compute the velocity for x, the velocity for y, the angular velocity, which is theta dot, and then phi dot, which is how fast our steering angle is turning. So the inputs to this system are going to be v1, which is going to be the wheel velocity, and v2, which is the steering velocity. And these equations, they look a lot less messy than the other ones, because I'm not including the equation to compute the wheel velocity, which would be v1. I'm just going to put wheel velocity here. But you would compute the wheel velocity in much the same way that you compute differential drive velocity, because they're both wheeled robots. One thing to notice, though, is that when we look at the velocity equations, they consider both the theta value and the phi value. So moving in the x direction is determined not just by the orientation of the car, but also the steering angle. So you can imagine as the car is turning, our velocity in the x direction might be slowing down. And the reason is that this value between the cosine theta and cosine phi is going to be getting smaller. And the same thing happens with y. When we look at theta dot, you can see that it's just sine of phi over L. So the orientation only changes while the steering angle is changing. And the steering angle changes, but we also again have to consider this L value. So if L is very small, then theta can change very quickly. If L is very large, then theta changes more slowly. And so over here on the right-hand side, the farmost vector here, or the farmost term, we've got this 4x1 vector 0, 0, 0, 1, and then v2, which is the steering velocity. So the reason that we have a 0, 0, 0, 1 vector here is that the steering velocity doesn't really affect x dot, y dot, or theta dot. So even though the phi itself is in these values, phi dot doesn't actually affect it. So if you're turning the car, at each individual step, you look at the overall value of phi, and that matters when computing x dot or y dot. But you're not looking at how fast phi is changing. And really, the only thing that is affected by how fast phi is changing is phi, the rate of change for phi. That's why we have this 1 down here at the bottom, and that's the only thing that's going to be multiplied by v2, and v2 is the steering velocity. So when we look at the difference between differential drive and car-like robots, when it comes to feedback, our feedback is largely the same. There may be some kind of minor differences, but in general, it's going to be the same to compute the odometry information and to get the speed of the wheels. But whenever we're computing the overall velocity of the system, or we want to control how it moves, we have to consider this additional angle, the steering angle. So we're going to take a brief detour and talk about degrees of freedom and configuration. So these two are not quite the same thing, but they're definitely related. Degrees of freedom is a degree of freedom is a parameter of a system that can be moved freely without moving another parameter of the system. So if you think about a point on a plane, it has some xy value. We can move it along the x. We can move it in the direction of the x-axis, and the x value is changing, but y is not changing. So x then would be a degree of freedom. And similarly with y, we can move it in the direction of the y-axis, but its x value will not change. So y would also be a degree of freedom. So when we talk about the degrees of freedom of a system, we're trying to think of all the parameters that we can move around without moving something else in the system. And a configuration is going to be the number of independent parameters that define a system's pose. A pose is a position and orientation. So a pose would be like those 3x1 vectors that were x, y, theta. That would be a pose. So a configuration is like saying we have this reference point on our robot, and but we acknowledge that there's the robot itself is much larger than a single point. So how do we compute all these other points on the robot that are not the reference point? A configuration of a system is like a vector that gives us all the values that we need to compute all the other points in the system. So typically, a configuration is just comprised of all of the degrees of freedom, the values for the degrees of freedom, but not always. And in robotics, it's not always the case, and when it's not the case, it matters. So I just want to introduce this topic. So okay, let's just go through some examples. So think of a point in a planar coordinate system, so a 2D coordinate system. How do we define its configuration, and how many degrees of freedom does it have? Okay, so we just talked about this one. Its configuration would be xy. So even though it's a point, we're kind of saying, oh, how do you compute all of its other points? Well, it doesn't have any, so you just need to consider the single point. So its configuration is xy. If we had just x, though, we wouldn't have enough information to compute the whole point, right? We need both the x and the y. How many degrees of freedom does it have? It has 2. X is a degree of freedom and y is a degree of freedom. So now if we change this to a spatial coordinate system, a 3D space, we have x, y, and z, then the configuration changes to x, y, z, and the degrees of freedom goes up to 3. So here is my quiz question. So think of a laptop moving on the surface of a table. So we have a flat table, and we're taking a laptop, and we can move it around. How do we define its configuration, and how many degrees of freedom does it have? So for this one, we have x, y, and a theta value. And so the theta value is how much the screen of the laptop is open. And so that means it's going to have 3 degrees of freedom. So you can move it like in the x direction or in the y direction, but you can also just unfold the top of the laptop and change how much the screen is open, and that doesn't actually change the x value or the y value of that laptop. So that would be included as a part of its configuration. And we need to know that information, right? Because the screen of a laptop is really important. So if we wanted to talk about the laptop as a whole, we would want to consider all the points that make up the screen. And if we don't know like the rotation value for how much the screen is open, then we wouldn't be able to to compute any information about it. So we have to include that as part of the configuration. Okay, so now we're going to talk about, okay, how does this relate to robots? So first, let's look at a car. How would we define the configuration of this car? So x, y, theta would be its configuration. So I'm realizing now that I actually left out phi. Okay, so sorry about this, guys. I've been recording for 32 minutes. I really don't want to start over. So here we have x, y, theta, and phi. So it should be phi here. So we should have 4 values. So we need to know x, y, theta, and phi. So how many controllable degrees of freedom does it have? So this is something we haven't yet introduced, but just think about, what can we control about this system, and how many of those things are degrees of freedom? So think about the inputs to the system. What are the inputs for a car? So for the car, we have 2 controllable degrees of freedom. One is the speed, and we control that by pressing on the accelerator. And the other one is the steering angle. Oh, okay. Sorry, you all. I was right. It is just x, y, theta, because phi is part of the controllable degree of freedom, not necessarily a part of the configuration. Okay, sorry. So this slide is correct. I was not wrong here. So when we talk about the configuration for a car robot, the answer is x, y, theta. And anyway, so for how many controllable degrees of freedom does it have? It's the speed and the steering angle. Those are the two things that we are controlling as a person who's like, controlling a car. So because of this, we say that car-like robots are non-holonomic. And so a non-holonomic system means that the number of controllable degrees of freedom is less than the number of degrees of freedom in the configuration. So let's go back one slide. So we have 3 values in the configuration, but we only have 2 controllable degrees of freedom. And so that seems kind of arbitrary, and it kind of is, but the way that it kind of manifests itself in our system is that we're going to be subject to some kind of motion constraints. Like we can't, we're not going to be able to just move in any way that we want to. And in car robots, I think most everybody can tell that a car can't just instantaneously move sideways. So if we have our car here on the left, it can't just directly move in the right direction. It's just physically impossible for the car to do that. In order to move into that kind of position here over on the right, the car on the left would have to turn its front wheels and drive up some, and then turn its wheels again, and then drive in reverse. And then depending on how well you did that, you might have to do it some more. But it can't move in the x direction without changing both y and theta. And I say x direction here, that's just because of the way that I set this little figure up. It's just the direction of the wheels. Or sorry, the perpendicular direction of the wheels. And so whenever we talk about motion constraints, we have to define them mathematically. It's not good enough to just describe them in words, like I'm doing right now. So let's take a look at how to describe these motion constraints mathematically. So let's look at differential drive systems. Differential drives are non-holonomic. They're actually subject to the same constraint, like the same type of motion that car-like robots are, like where it can't just move sideways instantaneously. So you are able to self-rotate the robot, and then move it and then rotate it back, and you can get there, but that's not good enough, right? Like if the robot has some orientation, say like orientation 90 degrees, it can't move along the x-axis instantaneously. It has to rotate and then move. So I have this equation up here in the top right, y dot cosine theta minus x dot sine theta. This is like the most common non-holonomic motion constraint in robotics. So very, very often what you'll see in, when you're reading about robots is someone will say, oh, I have this, car robot, or I have this, differential drive robot. It's non-holonomic and it's subject to this constraint. And then it lists this equation here. And this equation encodes how this robot has to move. And so you can rearrange this equation if you move the x part over to the right hand side and then divide by cosine. What it's actually saying is that y dot is equal to x dot tangent of theta. And so that actually makes sense here. If you look at this right triangle, this is just like me blowing up the little reference point and the orientation value sticking out. We have y dot over here and x dot on the bottom, and some theta value. Y dot is going to be equal to x dot tangent theta. So like if you did tangent of theta is going to be equal to opposite over adjacent, so y dot over x dot, and then you just rearrange them. And what you'll see is, y dot is equal to x dot tangent theta. And so what this means is that the robot is always moving in this way. So, y dot is always going to be equal to x dot tangent theta, no matter, what kind of motion you're doing with this robot. Just the physical structure of the robot can only move in this way. So anytime it moves, it's going to be satisfying this equation right here. And so this is a really important part of robotics because if you're trying to maybe solve a grid or something, you might say, okay, I want you to move up, and then move to the right, and then move left. But sometimes the robot just can't do it, right? So I can't just say, oh, if I'm a car robot, I can't just move up a few places and then start instantaneously moving to the right. It has to prepare, it has to prep for this. So that's where this stuff comes into play. So let's look at a car-like robot. Car-like robots are also subject to this constraint, but they're also subject to a second constraint. So the one that you're looking at right now, the normal non-holonomic constraint, this is about the reference point, so the back wheels. So the back wheels of the car are always moving with this equation, but we also have one for the front wheels of the car. So we're going to add a point right here, xf, yf, for x front, y front, and that's going to be the point in between the front wheels, and the front wheels are also moving subject to a constraint, and it's this new equation I listed here. It's basically the same equation, so yf dot cosine some angle value minus xf dot sine equals 0. The difference is in the angle value inside the trig function. So instead of only theta, we now have theta plus the steering angle. Okay, and so most wheeled robots are non-holonomic. I listed these here just to kind of loop us back to the beginning. Differential drive are non-holonomic, car-like robots are non-holonomic, skid steer are non-holonomic. Usually with skid steer, you have it's similar to differential drive, where you have like a left and a right side, but instead of one wheel, it's like two wheels. Or you could do like front and back, and it just depends. But those are non-holonomic, and this synchro, those are holonomic. They can actually, they don't really have many constraints on the directions that they can move in, but we won't really be working with those in this class. But you should just know holonomic mobile robots do exist. Alright, so to recap, the first thing we did was look at wheel encoders, and we used wheel encoder information to calculate the distance traveled by a wheel. And based on that, we were able to model the geometry of a differential drive robot and show how we calculate the change in position and change in orientation. We looked at control systems for differential drive and car-like robots, and we introduced the idea of a non-holonomic system. So in class next week, you're going to be coding a ROS node to actually compute the odometry based on the wheel encoder data. And then in the following week, we're going to start looking at global path planning for robotics.